and welcome back to the Fairbanks Museum Earth Science Lab. I'm Michael, and today we're going to be talking about steam power. And when you think of steam power, you probably initially think of human inventions, like this steam engine here, ways that human beings have been able to capture what we call steam power and use it to do work for us. However, in our natural world, there is a tremendous steam engine in our entire solar system that is keeping one of the most important processes on our Earth running. Without this great big steam engine that we have, life as we know on planet Earth could not exist. So it's extremely important, and in order to get a better understanding of how that natural steam engine works, we're going to go back to our steam engine model here and get a closer look at precisely how it works. So if you've seen my classes on energy and also my class on state changes, on freezing and boiling, you should be able to put together the pieces of this experiment and demonstration in your own head and really have a very good understanding of what we're going to be showing here. So I'm going to get the steam engine all set up, and I will come back to you when it's just about ready to begin, and I'll explain what you're seeing. So the boiler of the steam engine here, the tank, has been being heated up now for a few minutes by our alcohol fuel. So this machine uses as its source of energy the thermal energy that's being released by burning this alcohol fuel here. So if you remember from my energy class, you will know that there are many different types of energy that we experience in our universe, and the thing that binds them together, that groups them together under the idea of energy, is that they're all able to perform some kind of work to change their environment, and they can also be transferred between one another. Electrical energy can become mechanical energy. Thermal energy can become radiational energy. What we're doing here is we're taking our thermal energy from the burning fuel, using it to heat the water in the tank, and convert that heat into mechanical energy in our engine. So how does this work exactly? So if I were able to cut away this tank here, you'd know that you would be able to see some boiling water. This tank is only about a quarter filled with water, and we want it mostly air, because the entire idea of this system is to boil that water and to get it to turn from liquid water into water vapor. And that's where we're getting our mechanical energy from. Well, how does that work? So in this diagram of water molecules, you can see that when water is in its liquid state, all of its molecules are very closely bound together. They're virtually all touching one another, and if you can see that in between the H's and O's of the different molecules here, remembering that the water molecule is the two hydrogen atoms and the one oxygen atom that are bound together to make water. If you look here, hydrogens and oxygens of the two different molecules are bound together by what we call hydrogen bonds. This is what makes water stick together. We don't think of water as a sticky substance, but really on the molecular level it is. Water wants to stick to itself and stay together when it's a liquid, but when we heat up that liquid and turn it into a gas, all of those hydrogen bonds are broken. Those water molecules now want to be apart from one another instead of being close to one another. They split apart and they move away from one another, and we call this rarefaction. Rarefaction. That basically means that the water molecules are becoming more rare. They're splitting up from one another, and they're moving apart, and they're taking up more space. It increases the volume of water molecules in any space. So before we started to heat up this tank here, the water molecules were just at the bottom, all stuck together as a liquid. But now that we boiled that water, all of those water molecules have spread out into the air trapped inside of the tank, and they're pushing against all of the walls, even the top walls and the side walls, and they're trying to escape. That gas is building up, and it's pressurizing the tank in here. And if I open up the whistle there and let just a little bit of that water vapor, a little bit of that steam through, it wants to come up through the whistle and out, and that's what makes the noise. The second thing that's important about this rarefaction is that these water molecules, when they split up, they of course become lighter. 4 water molecules stuck together in liquid water is of course going to be heavier than 1 water molecule that has split up and flown off. So this gas, these separated water molecules, are very light, and they're always wanting to float up. They're lighter than the liquid water, and they're also lighter than the air in this room. That's why when you boil water on the stove, you see the water vapor rise and float up into the air. So this tank is pressurized because that water vapor, is very rare and trying to push out. And in particular, it's trying to push out in the upwards direction. So this pipe here out at the top of the tank is closed now, but we're about to open it, and we're going to let that water vapor through. It's going to push through with a lot of force, because remember, that water vapor is pressurizing the tank and it wants to escape. That water vapor is going to travel through this pipe around, and it comes out here at our piston. So this piston is another small tank filled with air with a little plunger in it. Ooh. That plunger is attached to this push rod, which moves the wheel. And you can see as the wheel moves, the push rod moves, and it's invisible to us right now because it's inside the tank, but that plunger is moving in and out along with it. So, if I open up the tank here, it wants to start, but it needs a little help sometimes. So because I was talking for a while, we actually evaporated most of the water in this tank, and we only got a little bit of action out of our steam engine here. I'll do it again so that you could see it a little bit more. But that water vapor was pressurized, and because we pushed it through such a small tube here, the pressure was very high. Whenever you're forcing gas or liquid through any kind of tube, the power that you get out of that forced liquid or gas is going to increase as the size of the tube that you're forcing it through decreases. So in such a small tube, we're able to force that gas through with a lot of power, and it's able to push that plunger, the piston, inside of this tank to turn the wheel here. So this is the type of steam engine that we're familiar with here on Earth, right? We have been using engines like this for hundreds of years in New England. And the engine itself can only last as long as your fuel lasts. Here I've burned out all of my fuel. There's no longer any flame here. That's why my engine shut off. So you could imagine if we had infinite fuel for our steam engine here, it could run forever. You would need not only infinite alcohol fuel, but you'd also need infinite water in this tank. But if you had those two things, this system could run forever. And if you remember at the very beginning of this demonstration today, I mentioned that there is a natural steam engine in our solar system that powers one of the most important cycles on our Earth, which is the water cycle. And that steam engine has almost infinite fuel and water to turn into steam. So now that we've seen this steam engine in action here, let's talk a little bit about that natural steam engine, because it's much harder to see than this machine right here. So if you were in my freezing and boiling class, you learned a little bit about the water cycle. The water cycle is literally a steam engine that works very similarly to this steam engine here. And so, of course, you probably know that the fuel that begins the water cycle, that starts the water cycle moving, is the fuel in the sun. The sun is our heat source that is really the similar thing to the alcohol fuel that we were burning here for this steam engine. Our sun has been burning for hundreds of millions of years at this point, and the fuel that it runs on is hydrogen, the very simplest element in our entire universe. It's taking those hydrogen molecules and under intense gravity is squishing them together to make helium. And when you take two hydrogen atoms and you stick them together, those two atoms bind and they become helium, which is a different element with well, it's the next element coming up after hydrogen. So that's something that we haven't really been able to harness on our own Earth yet. It's called nuclear fusion. Takes a lot of energy to do that, but that nuclear fusion energy that's being created by the sun throws off a lot of heat. And that heat reaches our Earth in the form of solar radiation. It has to travel thousands of miles through space to get here. But that heat energy that's being formed in the sun travels across space and warms up the surface of our planet. And the surface of our planet is, of course, covered 70% in oceans of liquid water. And that solar radiation heats up that water and causes it to evaporate. So the transfer of thermal energy that happens here in our steam engine happens between just a few inches between the flame from the alcohol fuel and the tank of water here. But the steam engine in our universe, that thermal energy has to travel thousands of miles through space until it eventually gets down to our Earth to heat up our water. But even though the distances between these two steam engines are obviously very, very different, they operate in almost the exact same way. So the heat from this fuel causes the water in our tank to boil. That liquid water turns into water vapor, and it rarefies and tries to escape the tank. The exact same thing happens on the surface of our Earth when liquid water in our oceans and lakes, and even from our own bodies and from plants, that water is heated, is energized by our solar radiation. It's turned from liquid water into water vapor, water gas, where it rarefies and then starts to float up into our atmosphere. So just like here, that water vapor is rarefying, and it's very light, so it rises up. And in our steam engine here, we captured that pressurized, rising gas to push this piston. That's the work that we were trying to do. In the water cycle, the work that's being done is literally the movement of water up into the atmosphere and then from place to place across the Earth. So as that water on our oceans evaporates and moves up into our atmosphere, of course it forms clouds up there as it recondenses in the colder, higher regions of the atmosphere. Wind pushes those clouds across the Earth, and that water will, when it condenses enough, turn back into liquid water. Those hydrogen bonds will reform. That water becomes heavy again, falls out of clouds, and then this water cycle restarts, but it only gets to restart because our fuel source, our heat source, is still going, right? As long as the sun is fusing hydrogen atoms into helium molecules, or helium atoms, I suppose. But as long as that sun is burning its fuel and creating heat, the steam engine in our atmosphere that we call the water cycle is going to continue to run. Water is going to continue to evaporate and move into the water cycle. So if our sun were to shut off, that would be the same thing as removing the alcohol burning fuel from our steam engine here. And so, of course, we know from being familiar with the steam engine that if we remove the fuel, the water is going to stop boiling and the engine is going to shut off, right? The exact same thing would happen to the water cycle here on Earth if the sun were to stop burning. If its hydrogen fuel source were to run out, the sun will fizzle out or explode, and that will end the water cycle effectively. So if that sun did go out, you would not have any more solar radiation coming to warm the Earth. So all of the water that is trapped here on our Earth is going to all come together in the oceans and lakes of our Earth, and it will never evaporate again, which means that we will never see any more rain, and it also means that over time, water is going to disappear from virtually every other place on Earth that isn't an ocean. So all of our wells would dry up because all of that water that we're taking up out of the ground is really recent rainwater. That's all flowing through the Earth, making its way down towards sea level and eventually into the ocean. So if this water cycle were shut off, it would be a catastrophe. It would dramatically change the entire Earth, and it would really dramatically change our human way of life. We rely on this large natural steam engine very much. But we don't have to worry about that source of fuel running out for a couple more 100 million years, it looks like. We've studied our sun quite thoroughly, and other suns in our universe also, and we know that nothing bad is going to happen to our sun anytime soon. So the other question in terms of asking whether our water cycle steam engine will be able to run forever or not is to think about whether any of that water is escaping the system. So remember, we said for this engine to run forever, we would need infinite fuel to burn, but also infinite water to put in the tank. Because eventually, as this engine operates, it has to release some of the steam that it creates. Otherwise, if we just kept building up steam and building up steam, the pressure inside of that tank would keep building up and building up and building up until eventually the entire machine exploded. And of course, we can't have that happen because, well, for obvious reasons, I suppose. So to keep that from happening, we have this little outflow pipe here. You probably saw that as this machine was running, you could see some water vapor escaping from here out of the system and floating up into the air. That's necessary for the system to run. Some of that water vapor was being forced into the piston to push the piston down, moving the crankshaft here in order to turn the wheel. But some of it has to be forced out. The water cycle actually gets around this problem, though. Our atmosphere actually traps all water on our Earth, in the air and on the ground. So as the water cycle runs, as that steam engine turns, all of the water that's being used is being contained permanently within the system. There isn't any water vapor that's being thrown out into outer space as the water cycle continues to work. So what this means is that if our sun did last forever, the water cycle would be able to keep going forever. You've probably heard that the same water that we use and drink today is the same water that the dinosaurs drank millions of years ago. And that is certainly true. Yes, the water that's on the planet today has always been here, and there won't be any more or less of it in the next couple thousand years as the water cycle continues to operate. So this steam engine that we have naturally here in our solar system is actually really fantastically well built. It's better built than any human steam engine has ever been. When we talk about engines and how well they run, we use the word efficiency. And efficiency is usually a measure of how much work the machine can produce given how much fuel and other supply, like water, that needs to be put into the engine. Our water cycle is extremely efficient. It essentially converts, well, it doesn't convert all of the solar radiation that comes out of the sun. Some of it gets blocked by the atmosphere, and some of it gets absorbed into dry things like rocks. But most of the solar radiation that comes from the sun gets converted into mechanical energy in the energizing of water and making it turn into water vapor. And then none of that vapor escapes, and the fuel source is very efficient and is going to last for hundreds of millions of more years. So our water cycle is more efficient than any human steam engine that's ever been built, which I think is really fascinatingly cool. And you can show yourself how wonderfully well built this steam engine is by actually setting up your own experiment at home, which is the water cycle in miniature. It's very easy to do. All that you need is a small bowl of water and then a nice tall glass vase that can fit around the bowl and capture it. So a kind of vase that has a flush edge, so that if you set it down on the table, it seats flat on the table to try to capture all of that air inside the vase. And if you take that little system, it's like a miniature atmosphere. If you take it and you put it on a windowsill or any place that gets direct sunlight, the sun over time, that same solar radiation that warms our ocean, is going to energize and warm up the water in your little bowl there, and pretty soon you'll see the water level in the bowl go down, and you'll see condensation forming on the inside sides of your vase. And I think that you've certainly learned enough from these demonstrations today that you can say exactly what's going on inside of that little experimental setup. You've basically created the water cycle that you can hold in your hand, and it works exactly the same way, using the exact same fuel source, the sun. So I hope that you all get a chance after watching this demonstration here to go out in your own home and do that experiment for yourself. So thank you all very much for tuning in to this experiment today with the Fairbanks Museum Earth Science Lab. Thank you very much.